In 1941, the United States Army Air Forces sat down and wrote a specification so extreme that it read less like an engineering request and more like a dare. They wanted an aircraft engine capable of producing between 4,000 and 5,000 horsepower. For context, the engine powering the workhorse Boeing B-17 Flying Fortress, the Wright R-1820 Cyclone, made about 1,200 horsepower on a good day. The Army wasn't asking for an improvement. It was asking for something more than triple the output of engines already considered massive. And the reason wasn't ego. It was geography. Planners were terrified of a scenario in which the United Kingdom fell to Nazi Germany, leaving America without a forward base from which to strike Europe. If that happened, bombers would need to fly from North American soil, cross an ocean, deliver their payload, and return, all without refueling. That kind of range demanded a new class of engine, one built around fuel efficiency at a scale nobody had ever attempted. So the Army took its specification and walked it around Detroit and beyond, knocking on the doors of the biggest names in American power plant engineering. One by one, the giants of American engine manufacturing looked at the numbers and walked away. The horsepower target was brutal enough on its own, but the fuel efficiency requirement made it worse, because building something that powerful usually meant building something that drank fuel at a catastrophic rate, and this engine needed to do the opposite. It needed to sip fuel across thousands of miles while producing more raw power than almost anything in the sky. Every company with the resources to attempt it took one look and decided the risk wasn't worth the reward. The hesitation made sense once you understood what these companies were already juggling. Wright Aeronautical was buried under demand for the R-3350 duplex Cyclone that would eventually carry the Boeing B-29 Superfortress across the Pacific, and it had no spare engineering capacity to gamble on an unproven power plant with a horsepower target nobody had reached before. Pratt Whitney was equally consumed, pouring its best engineers into the R-4360 Wasp Major, an air-cooled 28-cylinder radial nicknamed the Corn Cob for its distinctive four-row layout, an engine that would eventually power everything from the Boeing B-50 to early versions of the Convair B-36. Every serious engine manufacturer in the country was already stretched thin building proven designs at wartime volume, and volunteering to chase an unproven 5,000 horsepower target looked, to men running production lines under enormous pressure, like a distraction they simply could not afford. Curtiss-Wright, still fielding orders for its own radial engines across multiple aircraft programs, faced the identical calculation and reached the identical conclusion, leaving the Army with a shrinking list of qualified candidates and a widening sense of urgency as the calendar pushed further into the war. That left the job sitting on the table, unclaimed, until it landed at the doorstep of a company nobody expected, Studebaker. Studebaker was not an aircraft engine manufacturer. It was a car company out of South Bend, Indiana, a firm that traced its roots back to a wagon and carriage business founded generations earlier, and that had spent the interwar years building well-regarded sedans. During the war, that same factory floor pivoted to building the tough little M29 Weasel, tracked utility vehicle. Studebaker had space in its factories. It had engineering talent. And crucially, it had almost nothing to lose, because by its own later admission, the company had no real interest in becoming a permanent player in the aircraft engine business. This was a wartime obligation, not a strategic ambition. But someone had to build the thing, and Studebaker had the capacity, so the Army handed them the program, internally designated MX-232, and the clock started ticking. To lead the design, Studebaker brought in a veteran propulsion engineer named Norman Tilley. Tilley wasn't a stranger to oversized, unconventional engines. The engine that emerged from Tilley's drawing board was named the XH-9350, a designation that wasn't just a random string of numbers. It described the engine's total displacement in cubic inches, 9,350 cubic inches, which converts to roughly 153 litres. To put that in perspective, a typical modern car engine displaces around 2 litres. The XH-9350 displaced enough volume to swallow more than 70 of them. It was liquid-cooled, arranged in the H configuration, meaning it was effectively two flat, horizontally opposed 12-cylinder engines stacked one on top of the other and geared together to drive a common output shaft. This layout wasn't unique to Studebaker. The British had already gone down this road with the Napier Sabre, the H-24 engine that powered the Hawker Typhoon and later the Hawker Tempest, ground attack aircraft that terrorized German armor columns in the months following the Normandy invasion. Rolls-Royce had experimented with a similarly radical concept in the Chrysler, a sleeve valve two-stroke design that never reached production. But Studebaker was pushing the concept further than any of them, into genuinely uncharted displacement territory. The physical numbers were staggering. Each cylinder carried an 8-inch bore, an enormous dimension for an aircraft cylinder, paired with a bore and stroke ratio that Tilley's team had calculated down to the decimal to balance power output against mechanical stress. 24 cylinders in total, arranged across the two banks, a projected output of 5,000 horsepower, sitting right at the top edge of what the Army had originally demanded. And despite that almost unbelievable power figure, the complete engine was projected to weigh close to 7,000 pounds, a number that engineers were fighting to keep as low as possible, because every pound of engine was a pound that couldn't be fuel, and fuel was the entire point of this program. Building an H-block engine of this size introduced problems that simply didn't exist on a conventional radial or inline power plant. With two crankshafts running in parallel, one for the upper bank of 12 cylinders and one for the lower bank, the engine needed a gear train precise enough to keep both crankshafts perfectly synchronized under load, because even a tiny mismatch could translate into destructive torsional vibration capable of tearing the engine apart from the inside. The British had learned this lesson the hard way with the Napier Sabre, whose early production examples were plagued by sleeve valve failures and cooling problems so severe that entire squadrons of Hawker Typhoons were grounded, while engineers scrambled for fixes, problems that Napier didn't fully resolve until well into 1944. Tilley's team studied those failures closely, choosing conventional poppet valves over the more exotic sleeve valve arrangement that had given Napier so much grief, a decision that traded away some theoretical efficiency for a design the Studebaker engineers believed they could actually make reliable within the timeline they had been given. Cooling was its own nightmare at this scale, since a liquid-cooled engine producing 5,000 horsepower generates an enormous amount of waste heat that has to be carried away through radiators without adding so much drag or weight that it defeats the entire purpose of the aircraft it was meant to power. This wasn't a paper exercise dreamed up in a design office and left to gather dust. Between 1942 and 1945, Studebaker's engineers logged thousands of hours of dynamometer testing, first on single-cylinder test rigs to validate the fundamental combustion characteristics, then on twin-cylinder setups to study how adjacent cylinders in the H-block would interact under load. Real metal was cut, real components were machined, tested, refined, and tested again. A full prototype engine had been ordered and was moving through fabrication. This was as close to a finished product as an experimental aircraft engine of this scale could get, without actually running as a complete unit on a test stand. Somewhere in a Studebaker facility, technicians in coveralls were adjusting valve timing and recording data on an engine that, had it reached production, would have been the most powerful liquid-cooled piston aircraft engine the United States had ever built. The single-cylinder test work alone tells you how methodical this program was. Rather than gambling everything on a complete assembled engine straight out of the gate, a hugely expensive and risky approach given how many unknowns existed in a design this large, Tilley's team built individual test cylinders that mimicked the exact bore, stroke, and cooling passages of the final design, then ran them on dynamometers to measure combustion behavior, detonation limits, and thermal loading in isolation. Only once those single-cylinder results looked promising did the team move to twin-cylinder rigs, essentially a miniature slice of the H-block layout, to study how neighboring cylinders influenced each other's cooling and vibration characteristics. This staged approach, single-cylinder first, then twin-cylinder, then eventually a full prototype, was standard practice for genuinely novel engine architectures, and it explains why 3 full years passed between the project's start and its cancellation without a complete running engine ever turning over. Every stage generated data that fed back into revisions of the design, and every revision meant new parts had to be machined and tested again. It was slow, expensive, methodical work. The kind that rarely produces dramatic headlines but that separates a serious engineering program from a fantasy sketched on a napkin. Meanwhile, elsewhere in the country, a rival program was chasing a similar dream from a different direction. Lycoming was developing the XR 7755, an almost science fiction-looking radial engine with 36 cylinders arranged in 6 banks of 6, displacing an even larger 7,755 cubic inches. The Lycoming design would eventually claim the title of the largest displacement aircraft piston engine ever actually run in the United States, reaching 5,000 horsepower on the test stand in 1944 before reliability problems and the fast-approaching arrival of jet propulsion ended its story too. Studebaker and Lycoming were essentially racing toward the same finish line from opposite directions, one betting on H-block liquid cooling, the other on an air-cooled multi-row radial, and both racing against a war that was ending faster than anyone in Detroit or South Bend had planned for. The whole intercontinental bomber concept that justified an engine this extreme traced back to a request from General Henry Hap Arnold in the spring of 1941, made at a moment when German forces controlled most of continental Europe, and a British collapse seemed like a real possibility to American war planners. Arnold wanted an aircraft that could take off from Maine, strike targets in Germany, and return home without landing on foreign soil, a requirement so far beyond existing aircraft technology that it forced the entire industry to rethink what a bomber, and the engines powering it, could actually be. Convair answered that call with the earliest design studies for what would become the B-36, while separately, the Army pursued engines like the XH-9350 as a hedge, a way of making sure that whichever airframe eventually won the competition would have a power plant capable of matching its ambitions. The intended destination for an engine like the XH-9350 was never entirely settled, because the entire point of the program was flexibility for a future that hadn't fully taken shape yet. Convair was already sketching the earliest concepts of what would eventually become the B-36 Peacemaker, a bomber so large it would ultimately fly on 6 Pratt Whitney R-4360 Wasp major radial engines, supplemented later by 4 jet engines bolted under the wings. The B-36's designers, much like Studebaker's engineers, were obsessed with one brutal fact of physics, that intercontinental range meant carrying an enormous weight of fuel, and every ounce of that fuel had to be paid for somewhere else on the airframe. An engine like the XH-9350, with its promise of 5,000 horsepower delivered with genuine fuel economy, was exactly the kind of power plant that a hemisphere-spanning bomber fleet would have wanted in its inventory, whether mounted on a B-36-style behemoth or on whatever successor aircraft the Army Air Forces might have dreamed up next. But history has a habit of moving faster than engineering programs, and in the case of the XH-9350, it moved in exactly the wrong direction. The war in Europe ended in May of 1945. The war in the Pacific ended that August. And almost overnight, the entire strategic justification for a fuel-sipping 5,000 horsepower engine designed to fly bombers from Kansas to Berlin without landing simply evaporated. There was no more need to plan for a fallen Britain, because Britain hadn't fallen. There was no more need to plan around a Pacific War stretching into 1947 or beyond, because Japan had surrendered. The Army's original order for 6 complete prototype engines was slashed down to a single unit, a devastating signal to any engineering team that the program's priority had collapsed. And Studebaker, which had never wanted to be a permanent aircraft engine manufacturer in the first place, saw the writing clearly. The company wanted to get back to building cars for a peacetime American public that was hungry for new automobiles after years of wartime rationing, not continue pouring resources into a niche, unproven, and now strategically unnecessary power plant. In October of 1945, the XH-9350 program was formally cancelled. The drawings, the calculations, the accumulated engineering knowledge of 3 years of work were shipped off to Wright Field in Ohio, the Army Air Force's primary research and testing installation, where so many other cancelled wartime projects went to be quietly archived and largely forgotten. The physical hardware, the machined cylinder blocks, the test components, the nearly complete prototype that Tilley's team had been assembling is generally believed to have been scrapped. There was no dramatic unveiling, No test flight, no moment where the engine roared to life in front of assembled generals. It simply stopped, mid-stride, a 3-year sprint that ended not at a finish line, but at a wall nobody had seen coming. And even if the war had dragged on another year, even if Studebaker had finished that prototype and proven every one of Norman Tilley's calculations correct, the XH-9350 was already facing a second executioner waiting in the wings. Jet propulsion. While Studebaker's engineers were still fine-tuning valve clearances on their H-block giant, General Electric was rapidly advancing turbojet technology that would soon produce the J-47, an engine that would power the North American F-86 Sabre into combat over Korea and become one of the most mass-produced jet engines in history. Lockheed's P-80 Shooting Star, America's first operational jet fighter, was already flying by the war's final months. The entire premise that had justified engines like the XH-9350 and the Lycoming XR-7755 and even the earlier Napier and Pratt Whitney H-block experiments was the assumption that piston power would remain the only viable path to high-output flight for years to come. Jet engines shattered that assumption within an astonishingly short window. A finished, flying XH-9350 in 1946 would likely have been obsolete within 2 or 3 years anyway, rendered irrelevant, not by a design flaw, but by an entirely different branch of the technology tree suddenly bearing fruit. There is a strange twist buried in this story that makes it feel less like a dead end and more like a full circle. Studebaker didn't simply walk away from aviation power plants forever. During the war, the same company had been busy building Wright R-1820 Cyclone engines under license, the very engine family that powered the B-17 Flying Fortress, meaning Studebaker's factories had already been turning out reliable radial engines for Boeing's iconic bomber, even while Norman Tilley's team worked on the far more ambitious H-block design down the hall. What makes the XH-9350 worth remembering isn't that it failed. Plenty of wartime engineering programs failed, and most of them are barely footnotes today. What makes it remarkable is how close it came to succeeding, and how much genuine engineering discipline went into a project that history had already quietly scheduled for cancellation before it even reached its final testing phase. This wasn't a fantasy sketch or an unbuilt paper concept like so many other wartime what-ifs. Thousands of hours of dynamometer data existed. A prototype was under construction. Norman Tilley's team had solved real problems in cylinder cooling, crankshaft synchronization, and fuel delivery at a scale that few engineers anywhere in the world had ever attempted. They were, by every meaningful measure, on track to deliver a functioning 5,000 horsepower liquid-cooled aircraft engine, a machine that would have stood alongside the Napier Sabre and the Lycoming XR-7755 as one of the largest and most powerful piston aircraft engines ever built. Instead, the XH-9350 exists today almost entirely in archival paperwork. The XR-7755's survival was closer to an accident of storage than a deliberate act of preservation, and it took decades before restorers brought it back to a display-worthy condition. The XH-9350 was not so fortunate. Whatever hardware Studebaker had machined for its prototype never received that second chance. There is no flight test footage, no roaring dynamometer video preserved for aviation enthusiasts to watch online. What survives is a set of numbers, an 8-inch bore, 24 cylinders, 9,350 cubic inches, 5,000 horsepower on paper, 7,000 pounds of engineering ambition that never got the chance to turn a propeller in anger. It's worth sitting with the strange position Studebaker found itself in. A company built on manufacturing affordable cars for American families ended up as the last serious contender standing when the United States military needed the single most powerful aircraft engine ever attempted on American soil. Not because Studebaker was the most qualified or the most eager, but because every company that was supposed to be more qualified had already said no. Studebaker, a company that openly admitted it didn't even want the assignment, ended up producing 3 years of genuinely serious engineering work, hitting real technical milestones, and coming within a hair's breadth of fielding a working prototype, only to have the entire justification for the engine's existence vanish the moment the shooting stopped. If the war in the Pacific had dragged on even one more year, if Japan's surrender had come in 1946 instead of 1945, there is a real possibility that American long-range bombers might have eventually flown behind an engine that nobody expected a car company from Indiana to build. Instead, the drawings went into storage, the hardware went to the scrap heap, and the story of the biggest aircraft engine America almost built quietly closed its final chapter in October of 1945, just as the age of the jet engine was beginning to open its first. There is one more detail that makes the whole episode linger a little longer than most cancelled wartime programs. Studebaker itself didn't survive as an independent automaker for very long after the aircraft engine chapter closed. The company merged with Packard, the very manufacturer that had once turned down the same engine assignment Studebaker had been forced to accept in 1954, and the combined companies struggled through the following decade before Studebaker built its last automobile in 1966. So the two firms that had stood on opposite sides of that original 1941 decision, one refusing an impossible engine, the other reluctantly accepting it, ended up under the same corporate roof less than 10 years later, both eventually fading out of the automotive business they had spent generations building. Norman Tilley's name never became a household word the way Kelly Johnson's did at Lockheed or Alexander Kartvel's did at Republic, and the XH-9350 never earned a nickname the way the Napier Sabre or the Rolls-Royce Merlin did, despite representing years of serious, disciplined engineering by people who genuinely believed they were building something the world would eventually need. It simply exists as a set of blueprints and test logs, a reminder that some of the most demanding engineering achievements of the Second World War never got the chance to prove themselves in the sky, not because the engineering failed, but because the war that created the need for them ended before the machines built to answer that need were finished.